So let's look at how I got to that particular value of threshold. To do that, we're going to look at a little at the histogram calculation from Jupyter Notebook. Well, in fact, I'm not going to show you the whole thing. I'm just going to show you effectively one I prepared earlier. So this is the image. It's been loaded into Jupyter Notebook, and this is the histogram. So a couple of things. The histogram, this axis here of the histogram, of course, in this case is I've used 100 bins to produce this. So if you change the number of bins, you'll get different results. The number of bins in this case is not equal to the number of possible intensity values. I'm using I've specified having 100 bins, and then what Matplotlib does, which you have to be careful with, is that it finds the biggest value in the image array and uses that as the upper bin value, and then it divides the range between the lowest bin value and the upper into 100 bins. So that's what's happened here. I've used the NumPy histogram, the NumPy histogram routine rather than the Matplotlib version of the histogram. So I tend to prefer to do things using the NumPy histogram routine because I have full control over what's going on, and I can and what it gives me is a count for each histogram bin to say how many pixels fall into this range in terms of intensity, and it returns also the bin edges. So when we talk about bin edges, the histogram is collecting counts of intensities within a certain range of bins, a certain range of intensity values. So the bins are specified by the lower bin edge and the upper bin edge. And if you look at the documentation on histograms, you will come across this idea. This is what the histogram looks like, and you can see you can see there's kind of two broad peaks here. This corresponds to the pixels belonging to the brighter structure in the image, which is the leaf, and this little hill here corresponds to those belonging to grass. The sort of spikiness of the histogram is something that is investigated further in the practical. It has to do with a quantization effect, and a bin capturing either integer values of intensity, but either one integer value or two integer values, or two integer values and three integer values. And I can tell that in this case the bins are sufficiently wide to capture two or three integer values, and so one of these is higher than the spikes tend to be oscillating in such a way that neighboring histogram entries are 1/3 higher or 1/3 lower than the neighboring bins. So that's a quantization effect, which we'll talk about a bit more in the practical. So let's now go back to looking at the representation of this in the notes. So the histogram, if we were to produce a histogram in which the values of, we had a bin for each possible intensity, then this is the way that we would represent that. So that hash here represents count, doesn't represent hashtag. So it's a number of pixels such that the intensity values at those pixels is equal to intensity I. And that's a simple notation for how you would construct a histogram, where you have discrete values in the array F. So in other words, integer values in the array F, and you run through all the possible integer values and basically count how many pixels have that integer value. And this could be modified simply if you wanted to look for ranges of intensity values, which is effectively what the default Python code looks at. Now what we need to next do is to relate this the concept of the histogram, which of course everyone I'm sure understands what a histogram is, but we now need to think about how to relate that to a probability density function of intensities over pixels. So let's move on to into trying to capture that idea. So what I'm going to do is to first of all draw an axis for doing our our probability density function. So here is our axis, and what we're going to do is that along one axis here we are going to represent intensity by the variable x. So x represents intensity, and along this axis here, the y-axis, we're going to have p of x. So we're going to look at the probability density function of pixels, the probability density function of intensity across the image. Now, when we do this, normally the probability density function is something you only get to, a bit like expectation, by taking an infinite number of experiments. In this case, we've only got a finite number of pixels in the image. We only have one image, but so we're doing a bit of a hack here. But in doing this hack, I'm doing this hack in order to explain to you the notation of conditional probability and how you can think about things in conditional probability. So first of all, note that our the histogram of intensities, and I'm going to do a sort of not a very nice job of representing this, but let's say that our histogram, if we were to normalize it, I'll explain how to do that in a while, but our histogram basically looks something like this. Well, let's presume that our PDF looks something like this. Okay, and I've drawn this in a way that makes it relatively easy for me to sketch. So let's say that this is what, if we were to take our histogram, smooth it, and normalize it, we would get two bumps. That's what I'm trying to convey, two bumps in intensity. Okay, but the and you can do that with the histogram that I've shown you in the previous in the previous Python notebook. You basically need to smooth it and you need to normalize it. But let's say that we did that process, and we'll talk about how you do that a bit more later on. But the question is, how do we form a so how do we explain these two bumps here, and therefore by in explaining these two bumps, how do we then figure out how to set the threshold optimally? So that's what we're trying to do now. Okay, so first of all, we're going to introduce the idea of the conditional probability of intensities given only that we are looking at the background. So for background, let's draw the background in blue. And if we were to just take the blue pixels, sorry, the background pixels, and sketch their probability density function over intensity, we would get something that might look like this. So the way that we produce this is similar to the way we produce the green trace, which is we take the intensities of, so the green traces take the intensities, by the way, I should express what the green trace is. So the green trace is our P of x. So it's a probability density function of intensities for the pixels in the image. The blue trace is the same thing, but done only for the background pixels. Background pixels in this case would be the pixels belonging to the grass in the leaf on grass image. So this is, we denote that by P of x given B, where B stands for the background. And in this case, the background is grass. Okay? Whoops. So in fact, let's just get rid of that slash there. And let's just put quotes there. Okay, so that's the background or grass. Okay, so P of x given B is, and the way we get to P of x given B is, imagine you grabbed all the pixels that belong to grass. Now we have a slight chicken and egg problem because we don't have a method to do this yet. But conceptually, imagine that someone sat there and clicked on all the pixels that belong to the grass region, took all those pixels and then made a histogram of their intensities, then normalized that histogram and then smoothed it. This is what you would get, P of x given B. We can do the same thing for the pixels that belong to the leaf. So if we did that, we would get something that looked like this. So the pixels belonging to the leaf, which is our object, have on average a higher intensity than those belonging to grass. So I've sketched this pretty badly. You will discover that I'm pathetic at drawing. It's just and it also takes me a while to get warmed up with drawing every year. So just extend our axis out a bit like that. Okay, so this red curve is now the probability density function, conditional probability density function of P of X intensity, given that we're looking at object pixels. In this case, our object pixels, so O refers to object, and in this case that's going to be, it's going to be the leaf. Okay, now the choice of which thing is the object and which is the background is totally arbitrary, but I'm imagining that for some reason we want to detect the leaf on the grass, and so therefore in the, let's say, the language or the lingo of image processing or computer vision, we refer to the leaf as being the object and the grass as being the background. Okay, so now this P of X, the way that we define these things, or the notation I'm using here and the language I'm using here, is that of conditional probability. So P of X given B, whenever you see some expression that refers to probability and you've got this line here, you should read the line as given that. And so this is the probability density function over the variable X, which is intensity, given that we're looking at background pixels. So we're only looking at background pixels. And you read this in a sort of fancy way as P of X given B. This is the probability density function only of pixels that belong to the leaf, and we refer to that as P of X given O, where O represents our object or leaf. Okay, so that's a bit of sort of jargon for you. Okay, now how do we get from these the blue and the red, to this continuous curve P of X? So the way that we do that is we form what's called a mixture model. And the mixture model in this case is very sensible. Within this image, we've only got two types of thing. We've either got pixels that belong to the background, or we've got pixels that belong to the foreground. So we can explain the probability density function of all pixels, P of X, by making use to a two-component mixture model. And so our two-component mixture model is given by P of X, let's not use that color, let's use black for this. In fact, let's use green. So P of X is equal to P of X given B plus P of X given O. But we have one other thing to think about, which is that so P of X given B and P of X given O sort of stand on their own. But if we think about how we combine these two together, what we need to do is to combine them in such a way that we take into account the fact that we only have two conditions, and that the integral under this green curve should be equal to 1, because it's a probability density function. And one of the properties of a probability density function is that its integral should always be equal to 1. Similarly, each of these conditional density functions also has unit area under it. So to get these things to kind of normalize correctly, we have to multiply or scale each of these by the prior probability of finding a background pixel. And the way that the way to understand, so we multiply this by P of B, and I think in the notes I might have used PB for the prior probability of a pixel being a background pixel. But what does this P of B mean, and what is a prior probability in this context? It's very simple. So imagine you were to close your eyes. Again, remember our experimental space is just going to be this single image. So if you close your eyes and stick your hand into the image and pull out a pixel, okay, the probability that that pixel is a background pixel reflects the probability that in doing that thing of closing your eyes, reaching into the image and pulling out a pixel, it reflects the probability that you select a pixel that's a background pixel in that sort of blind sampling thing, okay? And so the prior probability is, in this case, has a very intuitive meaning, which is just the proportion of pixels in the image that belong to the grass region. And similarly, you have to scale this thing, P of x given O, by the prior probability of reaching into the image, pulling out a pixel randomly, and finding that that is equal to an object pixel. So it's basically the area of, as a proportion of the total number of pixels in the image that's occupied by the object pixels. And so that is our mixture model. And again, for this, I think I use P with a subscript O in the lecture notes. And the sum of these two is effectively, so if I were to sum this thing, I basically get this green trace here. So PB, by the way, P of B and P of O must sum to 1 because I only have two types of pixel in the image. It's either an object pixel or background pixel. So the other piece of information you need is that P of B plus P of O is equal to 1. Therefore, if we have a non-trivial image, both of these things are less than 1. So they're fractional, and therefore when you scale this by P of B, it shrinks down in height. And if you scale this red curve by P of O, it scales down in height. And then so the summation of these two will give you something that looks like this.